We've covered some of the fundamentals of water relations, what water potential is, and its components, as well as how water is transported in the tree. And we know that water is transported down a water potential gradient. In other words, water moves from less negative to more negative water potential. But how do those gradients of water potential get established? And I like to use this equation. It's a heuristic equation. That just means it's an equation that isn't necessarily mechanistically exactly correct, but it includes the important factors to help us think about how they interact in controlling water potential in, for instance, a leaf. So let's look at this where water potential of a leaf, for instance, is proportional to, that alpha just means is proportional to, and you can think of this almost as an equal sign, but the units don't really work out. So proportional to is the best way to think about that. It's proportional to soil water potential, so the water potential in the soil, minus transpiration rate times hydraulic pathway resistance. Now, we know what transpiration rate is, and we know what water potential of the leaf and soil is. We've learned about those. Hydraulic pathway resistance is just the resistance to water flow through the xylem of the tree. And we'll talk about that in more detail later, but for now, just understand that that's the resistance to water flow through the tree. So there's several implications of this equation. And one of them is if transpiration is occurring, in other words, if transpiration is greater than 0, then leaf water potential is less than soil water potential. In other words, leaf water potential is more negative than soil water potential. We know that's a fact both from looking at this equation. If this term, transpiration rate, is non-zero, if it's greater than 0, then this whole term here will be non-zero. We'll be subtracting something off from soil water potential, which means leaf water potential will be less than soil water potential. So that's mathematically, that heuristic tells us that. But we also qualitatively know that because we know that water flows from less negative to more negative water potential. So we know if transpiration is occurring, then we know that water is flowing down this path and that there's a difference in water potential between soil and leaf. Okay, so that's one implication. Another implication is that with constant hydraulic path resistance, so I'm just going to abbreviate this term as HPR, with constant hydraulic path resistance, leaf water potential becomes more negative sorry for my handwriting, as transpiration rate increases. Okay, so if hydraulic path resistance stays constant, so basically we don't need to worry about any changes in this, as transpiration rate increases, as this number becomes larger, leaf water potential becomes more negative. Okay, mathematically that makes sense because we know that as this number gets bigger, this whole number becomes bigger and we're subtracting a bigger number from soil water potential. So mathematically that works. Qualitatively it also makes sense because we know that flux equals the potential difference. We learned this last lecture. Divided by resistance. Okay, so in order, we know that in this case that's hydraulic path resistance. We know this is the same. So in order for this number to get bigger, this number has to get bigger. That potential difference is just the difference in water potential between the soil and the leaf. So as transpiration rate increases, that potential difference becomes larger. And then the third implication of this equation is that with constant hydraulic path resistance and transpiration, so if we hold transpiration and hydraulic path resistance constant, psi leaf will become more negative as soil water potential becomes more negative. The tree is rooted in the soil, and all other things being equal, will remain in equilibrium with the soil. So if these terms remain constant, then as this term becomes more negative, this term will become more negative. So in other words, as the soil gets drier, as the tree remains in equilibrium with the soil, its water potential will become more negative as well. So let's think about the implications of that heuristic equation that we just saw. Here's that equation. Let's think about its implication for variation in water potential across a 24-hour period. So this graph shows 5 a.m. to 5 a.m. over a 24-hour period. And we're looking at several panels. One is solar radiation here. This is transpiration rate. And then this is water potential of the roots and the leaves of a tree. So this is, a sunny day. We get a gradual increase in radiation and a peak around noon, and then a decline in the afternoon. And in general, transpiration rate, all other things being equal, tends to follow radiation pretty closely. So this is about what transpiration rate would look like on a day with radiation, sunlight like this. So think about then what should happen with, for instance, leaf water potential as transpiration rate varies. We're going to assume that soil water potential and hydraulic path resistance stays relatively constant. So as transpiration rate increases, leaf water potential should become more negative, right? And that's what we're seeing. As transpiration rate increases, leaf water potential becomes more negative because transpiration rate is increasing. After that peak in transpiration rate, we start seeing transpiration rate go down and we see leaf water potential become less negative. There's a little bit of a lag in the afternoon, basically as water catches up. But in general, that bell-shaped pattern of leaf water potential is an inverse of this transpiration rate pattern because of this relationship. We see a similar pattern in root water potential, except it's less severe. Okay, and we expect to see this. We expect for root water potential to be less negative than leaf water potential because water is flowing in this direction. and water always flows from less negative to more negative water potentials. So there's a water potential gradient within the tree as well. So that's how that relationship affects leaf water potential and root water potential relative to transpiration rate. We might hypothesize that, for instance, the water potential halfway up the stem, might look something like this. It would be intermediate to the root and leaves. Okay, so there's a gradient, so this is stem. So there's a gradient from the roots to the stem to the leaves in terms of water potential. Well, what would this pattern look like over a period of multiple days, for instance, when the soil is drying? This is sort of an exaggerated diagram showing what that might look like. So the graph we just looked at was 1 day. So for instance, maybe this part of the graph. Now we're looking at a period over about a week when soil water potential is declining. In other words, the soil is becoming more dry. Okay, so this term is becoming more negative as transpiration occurs and dries out the soil and there's no rain. So for instance, within a day, as transpiration rate occurs, the water potential of the leaves follows that pattern we saw on the previous graph, and does that every day. Okay, but what we're seeing is that over time, as the soil dries, both the water potential in the morning before transpiration starts, as well as the midday water potential in the middle of the day, is becoming more and more negative as soil water potential is declining. Okay, so that's sort of one prediction of this model. Now, we can measure water potential of trees using a pressure chamber, and we'll learn about that later in the class. But let's think about what happens when we measure water potential when transpiration rate is 0. Okay, so let's say this term is 0. We can think of that as being at night. There's little to no transpiration at night. So if this term is 0, that means, because these are multiplied together, this entire term becomes 0. And what that means is measures of leaf water potential when transpiration rate is 0 is roughly equivalent to soil water potential. So measurements of water potential of a leaf during that nighttime period when no transpiration is occurring is roughly equivalent to soil water potential. And that measurement is called pre-dawn water potential. That's a classic physiological measurement that people studying water relations often do. They go out in maybe 3 or 4 in the morning. The tree has had an opportunity to go into equilibrium with the soil. There's no transpiration rate. So a measure of water potential of the leaves at that point is roughly equivalent to soil water potential at that point in time. So this is an index of soil water potential. So that's a pretty common water relations measurement. Okay, at this point, there's a rain occurs on Monday morning. Soil water potential goes up, and the tree comes back is in equilibrium with the soil, and so its pre-dawn water potential goes back up to near 0, and the cycle starts again. So that's an example of a multi-day period of time illustrating these interactions between transpiration, soil water potential, and leaf water potential. We think about patterns of response to increasing soil water deficits or decreasing or more negative soil water potentials, scientists have classified plants into two broad classes in terms of what those responses look like: isohydric and anisohydric. So isohydric type plants, they regulate stomata and transpiration. When you regulate stomata, you regulate transpiration such that plant water potential remains relatively constant as soil water potential becomes more negative. So that's isohydric. And here's an example of an isohydric response. So all of these graphs are expressed as relative stress level. You can also think of this as being more negative soil water potential. Okay, so isohydric plants, you can see they maintain relatively constant leaf water potential as soil water potential becomes more negative. So then the opposite of that is anisohydric. Leaf water potential declines or becomes more negative as soil water potential goes down. Okay, so you can see that in the anisohydric, as soil water potential declines, the anisohydric has a more negative water potential. You know, broadly then we can think of this is the isohydric is basically a water conserving response. And that stomata are closing as the environment is becoming drier and water potential is regulated at the same, versus anisohydric, where you can think of this as a more risky response to drying. And that's sort of also then illustrated in these graphs where relative survival, as stress goes up, there's less mortality in the isohydric plants than in the anisohydric plants, because the anisohydric plants tend to keep their stomata open more, therefore their water potential becomes more negative as the soil gets drier, and they have a greater chance of losing turgor and dying. Now, another trade-off there is relative productivity. Because the anisohydric plants tend to keep their stomata open more as the soil dries, they're going to then tend to be more productive as the soil dries because they've keep their stomata open and they keep photosynthesizing. So there are trade-offs, maybe better survival for isohydric plants, but greater productivity for anisohydric plants as soil water potential declines. What I do want to say is that there's some back and forth in the literature about whether certainly there's a gradient or a spectrum in terms of the types of responses. There may be species that sort of fall in the middle of isohydric and anisohydric, and there also just are arguments about whether these classes, isohydric and anisohydric, even really exist, or whether they're just artifacts of other types of responses. But at any rate, it's one way to categorize plants and to think about contrasts in terms of, for instance, adaptation to drying soils and how those adaptations may differ between plants. But there's a lot of literature on these, and it's not settled by any means. So if we revisit this graph relative to that isohydric versus anisohydric pattern, this pattern is anisohydric. So that pattern I showed you is anisohydric because especially that midday or minimum water potential goes down as soil water potential goes down. So what would a isohydric response look like? So let's draw isohydric in blue. So let's say we had an isohydric plant. It might, on this day look like this, but as the soil dries, okay, it continues going down, but there's some minimum water potential and it regulates stomata to not go more negative than that. So as the soil dries, its pre-dawn water potential has to decline as soil water potential declines, but its midday water potential will remain relatively the same. Okay? So we just see a pattern like this. Okay, so eventually the isohydric plant will just not open its stomata because this is that negative water potential at which that isohydric plant is regulating its stomata. Okay, so that's sort of an example of how anisohydric and isohydric plants might differ with respect to their patterns of water potential as soil water potential declines.